Hello everyone, I am Dr. Siddheshwar Chopra and today we'll learn about a very important application in wave mechanics which is called particle trapped in a one-dimensional box. So herein we'll be revising many of the concepts what we have earlier learned. So let us get started. So this is a case of a particle in a one-dimensional potential box. So herein we have a particle trapped in a one-dimensional box. It is 1D box because the motion is taking place only along the x-axis. So let us assume the walls are rigid. The walls are at x equal to 0 and x equal to L. Having said that, L is your box length. Now, the rigid walls imply the potential here is infinity at the boundaries, and the particle does not lose energy while colliding with the walls. So basically it is an idealistic situation. Inside the box we have the potential to be equal to 0, and there is where our particle of mass m is lying. The idea of this derivation is to find the eigenfunction specific for this system, eigenvalues, which are the energy eigenvalues, probability density once we know the eigenfunction, and expectation values of the position and momentum. So let us get started now. So in this case, we use the time independent Schrodinger equation TISC, and which is written as T plus V on psi is equal to E psi. We are using time independent here because at a snapshot, at a single moment of time, we are finding the energy eigenvalues and wave functions. So that is what we are going to do here. So once we know what is T plus V is basically your kinetic energy plus the potential energy. We already know what is time independent Schrodinger equation, that is minus h cross square by 2m d square by dx square plus V psi is equal to E psi. But please pay attention here, we are talking about a particle which is trapped inside a box. So we are bothered about the portion between the region 0 to L. So in that region, V is equal to 0. So we have here the equation rearranged as d square psi by dx square is plus 2m e by h cross square psi equal to 0, which again we can write in terms of k square as d square psi by dx square plus k square psi is equal to 0. This is equation number A. Now this k is the wave number which we earlier understood, and p was equal to h cross k if you remember. Now the solutions of the equation A, which is a differential equation, for finding the solution of this equation we need to have boundary conditions and general solution. These two things are very important to get started with the derivation. So boundary condition is easily understood from the concept of wave packet. If you see at the boundaries or the at the infinite uh, distance, minus infinity to plus infinity, the wave function must decay. It must go down to 0. So that is what is the boundary condition we will be using. So in our case, the boundary conditions are psi at x equal to 0 should be 0 and psi at x equal to L should be 0 again. And the general solution seems to be a linear combination of e to the power ikx and e to the power minus ikx. So it is a e to the power ikx plus b e to the power minus ikx. Why we are having these combinations? Because if you see, e to the power ikx takes care of the wave traveling in the positive x direction, and e to the power minus ikx takes care of the wave traveling in the negative x direction. And you see here we have not taken any time dependence in this case, so there is no t factor here in the general solution. Now using the boundary condition, let us solve the equation. We substitute the first boundary condition psi at x equal to 0 is equal to 0 in equation number 1. So we get b is equal to minus a. That is the first result. Now using the second boundary condition and b is equal to minus a into the equation number 1 again, I find a e to the power ikl minus a e to the power minus ikl is equal to 0, or 2ia sine kl is equal to 0. So this is what we get once we have b equal to minus a and psi at x equal to l equal to 0. So now if 2ia sine kl is equal to 0, so what can be the solution? Either it can be a equal to 0 or it can be sine kl equal to 0. Now if a was equal to 0, then if you go back here, you will see b is equal to minus a in equation number 1. So if a is equal to 0, then psi will become 0 inside the box, which is not possible because we already said that the particle is present inside the box. So a cannot be equal to 0. If a cannot be equal to 0, then sine kl must be equal to 0. That is the only possibility left. In this equation also, it is very important to understand. Now we have kl is equal to n pi, and n will be integer starting from 1. But n cannot be equal to 0 again. If n is equal to 0, then kl will become 0 or sine kl will again become 0, indicating again there is no particle inside the box. So it has to be n not equal to 0. Now k is equal to n pi by l from this equation. Substituting for k equal to n pi by l in the formula k square equal to 2m e by h cross square, we get energy eigenvalue to be n square h square by 8 ml square. This is a very important formula. Now En is the energy eigenvalue and is discrete in nature. At n equal to 1, E1 is called the 0 point energy and it corresponds to the ground state. Now psi is equal to psi n, which is eigenfunction. Now please have a look here carefully. We are mentioning En instead of E because now energy has to be associated to every single energy level. So n is the index of the energy level we are talking about. So similarly, same thing holds good for psi. So for every energy level, there is a separate psi. So we will be denoting it by psi n. So which is your eigenfunction. And now using the boundary value calculations and finding the k, now we have the psi n, which was equal to 2ia sine kx. Now we can replace this entire constant value with some normalization constant because we will be normalizing our wave function to confirm if it is already normalized or not. So let me assume this to be some normalization constant n, and let me substitute k is equal to n pi x by n pi by l. So I have my final eigen solution to be eigen wave function to be n sine n pi x by l. So let me denote this sine of n pi x by some psi n dash. So I am writing it as n psi n dash x. So now the normalization condition we already know by now is integrating over the entire space and integrating this wave function should be equal to 1. Now please see here, once we multiply the normalization constant, this psi nx is the normalized wave function. So the normalized wave function should always give me 1 at the output here after the integration. Now let me substitute for my condition here of the particle in box of length L. So I will be integrating from 0 to L, and let me open up psi n star in terms of psi n dash. So I get n psi n star dash times n psi n dash dx is equal to 1. So basically the normalization constant we can easily get by integrating this particular thing here, and then you have 1 by root of integration from 0 to L psi n star dash psi n dash dx, which will turn out to be root of 2 by L. So this is a very simple mathematics involved here. You can integrate and you can get the value of normalization constant to be root of 2 by L. Once we know the normalization constant, it is very simple to find the final solutions for particle in 1D box. The eigenfunction primarily will be psi n x is equal to root of 2 by L sine of n pi x by L, where n starts from 1. And eigenvalue are En which is equal to n square h cross square pi square by 2 ml square, or n square h square by 8 ml square. The probability density, once we know the eigenfunction, becomes equal to mod of psi n square, which is 2 by L sine square n pi x by L. So that is all for today's lecture. Thank you.